Okay, so we're looking at a chunk of the alkanes topic today. So what I've got in front of me right now is the specification. And if I just zoom out slightly so that you can see it sort of like, well, it's not that this is most of it. So if I turn over, we've got basically it's split into three parts: fractional distillation, cracking, and combustion. And then if I go on to the next page, we can see chlorination. So this video is going to deal with everything on this first page, so fractional distillation, cracking, and combustion. And a different video, a separate video, which I'll link in the description, deals with the chlorination of alkanes, but which will be called, or will be focused on free radical substitution. So the video will be referencing free radical substitution more than it will be referencing chlorination of alkanes. So going back to what we're looking at today, first thing to say is you've done quite a lot of this actually at GCSE, even if you did combined rather than triple. You did you did alkanes themselves, and you had learned about them having a general formula of CnH2n plus 2. We're not really going to worry about general formulas anymore because they're only of limited use. So for example, when you come and do alkenes and you look at the general formula, maybe think back to the GCSE and what the general formula was then, which was CnH2n. That's no longer very useful because that's also going to be the general formula of a cyclic alkane. So I wouldn't really worry too much now about general formulae. But anyway, you did fractional distillation of crude oil. You did cracking, or the modification of alkanes by cracking, and you did combustion of alkanes. So all of those things were topics in the GCSE. And what I'd say about the A level is that it only takes some of those things a little bit further. So we're really building on what you hopefully already know or hopefully already remember. And really, I guess the new bits, for example, understanding the reasons why the different alkanes have different boiling points, which is the way we can separate them. That's probably more likely to be the area where you're likely to get assessed. But we're going to look at each of them in turn. So we're going to start with fractional distillation. So again, thinking back to GCSE, distillation and fractional distillation were methods of separation. So you did chemical analysis and you did something called separation of mixtures. And that basically is a way of separating things that are not chemically combined via some difference in their physical properties. Now that difference in physical property could be boiling point, which is what we're dealing with here. It could be solubility, it could be density, anything that we think of as being a physical property of a substance. So we're going to look at fractional distillation. Now before we look at the actual fractional distillation, so you're going to see a picture of a fractionating column very similar to the one that you should have seen or would have seen at GCSE. We're just going to consider first something that isn't sort of particular to A level, and that is why and how they have a difference in boiling point. And this very much connects or relates with the bonding topic in the course, so the physical chemistry bonding topic, where one of the things that you looked at or will look at, depending on when you're doing it, is intermolecular forces of attraction. So whereas at GCSE you just simply referred to weak forces of attraction between molecules, now at A level you have you break those intermolecular forces down into three types: van der Waals forces, permanent dipole-dipole, and hydrogen bonding. So that was in the bonding topic. So if we go now to consider some alkanes. So we've got three, and if we just sort of name them, we can see the first one. They're straight chain. They're all straight chain in these, starting with in these examples. And we've got three carbons to begin with. So we've got propane. Then we've got 4 carbons. We've got butane, and then we've got 5, which is pentane. And then if we consider what the MRs are, for propane it's 44, for butane it's 58, and for pentane it's 72. So what we've got is that we've got an increasing MR when we go from propane to butane to pentane. And if we're to look at the boiling points, one of the things that we notice is that propane has a boiling point of minus 42 degrees Celsius. Butane has a boiling point of minus 0.5 degrees Celsius. And then finally, pentane has a boiling point of 36 degrees Celsius. So we can see that there is a marked difference between their boiling points. And so one of the things is when you're considering the strength of any forces of attraction, right, whether it's metals, ionic compounds, or what we've got here, molecular substances, then really the boiling point or the melting point is your proof, is your evidence of the strength of whatever forces of attraction it is that you overcome when you change state. And when we're changing state with molecular substances like these, then what those boiling points are telling us, or what those changes of state temperatures are telling us, is how strong or how weak, whichever it is, the forces of attraction are between the molecules. So we only require a temperature of minus 42 degrees Celsius to overcome the forces of attraction in liquid propane. So those forces of attraction between propane molecules for it to become a gas. We need a greater temperature, so we need more energy for butane, and there's an even greater temperature and therefore more energy for pentane. So what this is telling us or showing us is that the forces of attraction are increasing as the length of the chain increases, or another way of putting it, the forces of attraction are increasing as the MR is increasing. So if we're thinking about how we would sort of explain that, or what reasons we would give, we've got to consider the possible intermolecular forces. So every molecule, or every molecule, but this would also include the noble gases. So even though they're not molecular, they're just simply separate atoms, we would still include that here. They all have van der Waals forces of attraction, right? They all involve temporary induced dipoles. Now, the full explanation of that is in the bonding topic, so I'm not going to talk too much about it, but all molecules have van der Waals forces between them. What we then have to decide is whether we also have, in addition to those van der Waals forces, whether we have permanent dipole-dipole or hydrogen bonding. And that depends, permanent dipole-dipole depends on two things. The first thing is that you must have at least one polar bond. So that means you have a noticeable difference in electronegativity between two covalently bonded atoms. So that's where you get your delta plus, delta minus. That's the first thing. But then coupled with that, that's not in itself is not enough to have permanent dipole-dipole interactions. Then you must also look at whether there is a net dipole, so whether there is an overall dipole in the molecule. The reason that you need the second as well is it is possible to have a substance with multiple polar bonds and they actually cancel each other out. There is no net dipole. So that's one of the things you've got to consider. And then when it comes to hydrogen bonding, which is essentially an extreme version of a permanent dipole-dipole, but it has its own name, you must have hydrogen bonded to oxygen, nitrogen, or fluorine. And again, you must also look for whether there is an overall a net dipole. So you've got to consider whether any of the dipole, if you've got more than one polar bond, whether they cancel each other out. So when it comes to alkanes, though, we only have van der Waals forces to consider. And so one of the things that you hopefully learnt when you did the bonding topic is that the larger the molecule, the greater the MR, the more electrons, therefore the greater the van der Waals forces. So here what we've got is our intermolecular forces are increasing. What we've got is the larger the MR, the more electrons there are. Therefore, the greater the van der Waals forces. between the molecules. Okay, between the molecules. So that is by far the most important thing to consider when comparing the boiling points of alkanes. You first of all check their MR. The MR is a correlation with the number of electrons. It's not the MR specifically, it's the number of electrons, because remember that temporary induced dipoles exist or come into existence because of the movement of electrons. So you get these temporary dipoles, these temporary delta plus, delta minuses. So the larger the MR, the more electrons there are, the greater the temporary induced dipoles there will exist or be, and therefore the greater the van der Waals forces between the molecules. So you first of all look at the MR. Now, sometimes when you do that, what you discover is that in fact you could be comparing 2 molecules or 3 molecules with the same MR. So when that happens, we have to consider something else. So if we look here, these are all isomers. So we've got pentane, and then we've got a branched version, and this is going to be methyl butane. Now we don't have to put the 2 in front here because the methyl can only be on the second carbon. Even if we did it, even if I'd done the methyl group here, I would be counting from that end of the chain, so it'd still be the second carbon. So there's no need for the 2, so I don't need to say 2-methyl butane, it's just methyl butane. And then the final one here is dimethyl propane. Again, I don't have to put a number, I don't have to say 2,2, because this is second carbon is the only carbon that the methyl groups can be on. Now, they all have the same molecular formula, they're all isomers of each other, so they all have the same MR. However, they do not have the same boiling point. So pentane, as we've already seen, has a boiling point of 36 degrees Celsius, methyl butane 28 degrees Celsius, and then finally dimethyl propane 10 degrees Celsius. So what we can see now is we do have the same MR, so we do have the same number of electrons. However, we do not have the same boiling point. And if we look at what's happening here, as the branching increases, or as there is more branching or greater branching, the boiling point decreases. So the intermolecular forces, the van der Waals forces, are less strong. Now, this can't be to do with the number of temporary induced dipoles, because we would expect there to be the same in all 3 because we have the same number of electrons. So there's obviously another factor. And the term that you have to use, the phrase that you have to use is about, or the thing that we're relating this to is contact surface area. So if we're comparing why straight chain isomers have a greater or higher boiling point, than a branched one, and remember this only matters when you're comparing molecules of the same MR. If they're molecules of different MRs, you absolutely just focus on the number of electrons or the MR. So this branching only matters when you're comparing molecules of the same MR. Then what we discover is that straight chain isomers, because these are isomers, that's what we're comparing here, is isomers of the same molecular formula, different structural formulae. Isomers have, and then we use the phrase greater contact surface area. That is compared to their branched isomers. And therefore the consequence of that is that they have higher boiling points. So this is one area where the physical chemistry side, the organic side can meet, where you can have questions where it seems to be about an organic topic, but actually its explanation or the description or thinking is to do with what you've done in the physical chemistry in the bonding section. But when it comes to alkanes, or I mean, or actually anything else, but when it comes to alkanes and you're comparing the boiling points, first of all, you look at the MR, and then if the MRs are equal, then you then look at branching, and then these are the explanations for why you get those differences in boiling points. Okay, so we look at the fractional distillation itself. So one of the things is that we've established now that the larger the molecule, the higher the boiling point. But it's important to remember that actually what's happening in our fractional distillation isn't so much about boiling, it's about condensing. So what we've got is we take our crude oil, which is a mixture, and our crude oil is vaporized. So to all intents and purposes, it's turned into gas. Now, some of it, there will be a residue. That residue will just get distilled further, will get distilled off it at lower pressures. But what we've got is we've chiefly got gases rising. So we vaporized our crude oil, and we've got gases now rising. Now, those gases are the different components of the crude oil. So some are short chain molecules, some are long chain molecules, and so on and so on. So they all have different boiling points, which means they condense at different temperatures. So boiling point, condensation point, they're exactly the same thing. It just depends on which direction you're going. So if we've already got the gases, those gases are going to condense to become liquids, and then when they're liquids, they're going to come off, as it were, right? So they're going to be sort of extracted. So what's happening at each of these sort of different temperature ranges is those fractions, or the molecules in those fractions, are condensing. So when we're talking about fractions, we're talking about portions, small portions of the crude oil. So if we look here, you can see that there's a range of number of carbons. So the molecules with those numbers of carbons are going to condense and be in the first fraction, and then the second fraction, and so on. Now, we've got this happening at different temperatures, and that's because what we've got is a temperature gradient. All right, so clearly we're vaporizing the crude oil, and it's hotter at the bottom, and it is cooler at the top. Right, so it's hottest at the bottom, cooler at the top, and we have in between, we have a temperature gradient. So as the gases rise, the temperature is decreasing, and once they reach their condensation temperature or condensation point, they condense, and so they're extracted off because of their different physical properties, because of their different boiling / condensation points. So the crude oil, let's just do it again. The crude oil is vaporized. So crude oil is a mixture. That vapor then passes into a tower. You've got a hotter bottom and a colder top because, if you even just think about having a fire in a fireplace and a chimney, obviously it's cooler at the top of the chimney than it is down at the bottom. So we've got a temperature gradient. So our gases rise, and then we've got these gases are different molecules with different MRs, so they have different boiling points. Those boiling points are the same as condensation points. So the larger the molecule, the higher the boiling point, the higher the condensation point. So, but don't forget, we are cooling down as we go up the column. So the larger molecules are condensed towards the bottom of the tower, and the smaller molecules, well, in fact, they don't even get condensed in the end because some of them remain as gases based on the temperature in the column. So that's all that fractional distillation is. It's a separation technique. It's based on physical property, which is the boiling point. Really what we're looking at is the condensation point. It's the same temperature as the boiling point. It just depends whether the only difference is you're going from a gas to a liquid rather than a liquid to a gas. So we vaporize our crude oil, into gases. Those are now going to rise. When they reach their condensation point, they condense. If they don't, they carry on rising, and they carry on rising until they reach the condensation point. And that is how we separate crude oil into fractions. So it's not one individual type of molecule, or size molecule rather. It will be discrete fractions, so portions of the mixture are basically condensed off. Only other thing to say maybe about the carbon chain and properties. So these are also physical properties. There's a difference in viscosity, so you can think of that as runniness, although don't use the word runniness. So the longer the carbon chain, the more viscous it is, and the less easily it runs. We can explain that now. We can explain that through an idea of intermolecular forces. Longer chain, stronger intermolecular forces, more viscous it is. And then other properties are the longer the chain, the harder to ignite, the less volatile, but then volatility is really connected with the boiling point. So how easily it evaporates as a way of thinking about volatility. And as we've already said, higher boiling points. And so that covers our fractional distillation. Okay, so now we come to cracking. So there isn't really a great deal to this, and this probably is one of those areas where, in a sense, it's about recall. It's about remembering the little specifics, the little details, the conditions, basically, that cracking has to undergo. So we'll talk about cracking a little bit in a second, but just want to highlight that really what you're going to have to remember is that there are two sets of conditions for cracking. And that what they're going to do is they're going to produce slightly different products. So we're going to look at thermal cracking very briefly, and we're going to talk about the fact that it's really, if what we want is alkenes, that's what we're going to focus on. And then we've got catalytic cracking, and that is if we're more focused on fuels and other types of hydrocarbons other than alkenes. So cracking in a nutshell is when you take a large alkane and you basically break it apart, and in the sort of most standard version is you break it into a smaller alkane and an alkene. Now, on the just previously we looked at fractional distillation, and we saw how we separated the crude oil into different fractions, so larger molecules, smaller molecules, and so on. Now, some of those are more in demand than others. So we can have, if you like, a surplus of some of the larger molecules. We have more than we actually have a direct use for. And so we want to, and we might not have enough of the smaller ones, the ones that we may use, say, for fuels or so on. We don't have enough of those. So there's a difference in supply and demand. And what cracking allows us to do is to take the things that we have too much of, to help satisfy the demand of the things that we have too little of. So we have perhaps more of the large molecules than we need, and so we can use cracking to make more of the smaller molecules that we do need. If we look at this sort of very basic general word equation, one of the things to use this as a way of highlighting is a particular type of reaction. So in chemistry, they can ask you about types of reaction, and this particular one is a decomposition reaction. Now, decomposition reactions are not exclusive to cracking. So how can we recognize a decomposition reaction? Well, it is actually quite straightforward. When you think about it, once you understand what it is that you're looking at. What we've got a single molecule on the left, and we've got more than one molecule on the right. So we are having something being broken down into smaller parts. Okay, so this is an example of a decomposition reaction. So I guess we can add that, right? So it's a decomposition reaction. Now, you may have used decomposition or heard of it or whatever before, and you almost certainly, when you did, had in front of it perhaps thermal. So you actually called something a thermal decomposition reaction. So the decomposition is the type of reaction really, because we're taking a single molecule and it is being broken down into sort of multiple molecules. So it's decomposing. The thermal was because in the example that you used that term for, it was being done through heating. So if decomposition is being done through heating, then it's thermal decomposition. Now, when we look at, you can just see the table below, and it's got two types of cracking, thermal and catalytic. Well, when you look at them, both of them actually involve high temperatures. So arguably, they're both thermal decomposition reactions, but really the important bit is the decomposition bit. Another area where you have done decomposition before, but maybe haven't realized or it wasn't pointed out, was electrolysis. So you took something like sodium chloride and through electrolysis you created, if it was molten sodium chloride, you made sodium and chlorine. You were taking a single substance, sodium chloride, and breaking it down into simpler substances, sodium and chlorine. So the thermal bit is just if you've done it through heating. Electrolysis was not through heating. This one will involve heating. But decomposition is when you're taking a single substance and breaking it down into simpler parts. So if we give an example, and this is just an example of what of a reaction that could be like this. We could take an alkane like decane, so C10H22, and that could be broken down into hexane, and then possibly, and just for this example, 2 molecules of ethene. So one thing that can come up in questions, I guess, is that and it would really only be a very simple sort of, when I say simple question, I mean in the context of the whole A level, by the time you're getting to the end of year 13, they could ask you to complete an equation like this to ensure that it's balanced on both sides. But we can see in this example, we've got a large alkane and we're breaking it into a smaller alkane and an alkene. Now, the two types of cracking, thermal and catalytic, I'm afraid you do have to remember these conditions. Thermal cracking, you've got a particularly high temperature, you've got a particularly high pressure. What that does do is that increases the cost. Okay. Pressure in particular is expensive. So you've got a high cost there, so there's an economic factor. So why are we bothering to do it instead of catalytic cracking, which we can see is certainly at a lower temperature, and the pressure is basically atmospheric, slightly greater pressure, but not much. And why are we doing that? Because we actually get different products. So we're going to get alkenes if we do the thermal cracking, and they are useful for making polymers, so addition polymers. So they give us the raw materials for addition polymers, which you'll do more about when you come to the alkenes topic. So that's like a chemical feedstock. So you might have heard that term chemical feedstock before, because I think at GCSE it would have been used. Whereas at catalytic cracking, we can see it's a lower temperature, but still quite high. It's almost normal pressure. We've got our catalyst. You have to remember the fact that it's a zeolite. What we're getting more of this time are fuels. But really, I mean, that's it, right? With cracking, you've got to sort of understand fundamentally what it is. It's useful to recognize or remember that it's an example of a decomposition reaction. But really, I guess the crux of it, and the thing which is slightly more than what you would have done at GCSE, is actually the conditions for two types of cracking. And I'm afraid you just have to remember those for an exam question. Okay, now we look at the combustion of alkanes. So initially, when it comes to the chemical equations, the chemical reactions that we might have to draw or write, then we're going to look exclusively at the alkanes themselves. But then we're then going to consider what the reality of a fuel a fossil fuel is and how other products could be formed in addition to what we'll look at in terms of the actual combustion of the alkane. So we're looking at alkanes as fuels. So the reason that they're useful is because the combustion of them is very exothermic. So a lot of energy is released. So energy can be transferred and used to and can be used in a useful way. We can get combustion. Again, this is probably like something that you did at GCSE, where we could have complete or incomplete combustion. So we'll consider those. And then when we're looking at actual combustion in terms of in an engine, then we can get a variety of different pollutants, including nitrous oxides and carbon monoxide and so on. So we'll just look briefly at that. And then one thing that is absolutely brand new, and which again is just it's a sort of single point in a way, but how, well, you probably know from GCSE that one of the pollutants is sulfur dioxide, but actually how we can remove that. So if you look at what it says at the bottom here, what students should be able to do is explain why sulfur dioxide can be removed from flue gases. So that's just the flue gases are the gases that are produced from the reaction. And then we're just going to look at the actual reaction that can take place. We're going to use either calcium oxide or calcium carbonate to remove that sulfur dioxide. So that's really a new bit, I guess, compared to what you've done at GCSE. All right, so if we look at the combustion of alkanes, we're going to start with complete combustion. Something to say and straight away is the fact that we can again make a connection with another topic that we've done, a topic that you've done in the physical chemistry side, which is about energetics. So one of the things that you looked at was the enthalpy of combustion. And if we look at the definition for that, we've got the change in enthalpy when 1 mole of a substance is completely burnt. All right, so the completely burnt part that we have here is our complete combustion. And when we have the complete combustion of an alkane, then we are looking at products of carbon dioxide and water. So if you completely combust any alkane, you will simply get as products carbon dioxide and water. So if we pick a sort of a simple example, if we pick the simplest alkane we can, so we'll pick methane. So if we do that, we're going to combust 1 mole of it. So methane there, CH4. For the moment, I'm just going to put oxygen and we'll balance it in a second. That's going to produce carbon dioxide, which is a gas. And then it's also going to produce water, which we're going to treat as a liquid here. Now, when it comes to balancing, and I'll do this a second time, one of the useful things is that whatever number of carbons you have, that has to be the number in front of the carbon dioxide, because the carbon only is present in one thing on both sides in a complete combustion, and that's your original alkane and your carbon dioxide. So we've only got 1 carbon in methane, so we don't need to put a number in front of our carbon dioxide. And the same with the hydrogen. All of the hydrogens in our water have to have come from our alkane. So we have 4 hydrogens in our alkane. We currently only have 2 in our water. We need to double that. So we put a 2 in front. And so you should always do the oxygens last. So because the reason for that is that whilst oxygen only appears in one thing on the left-hand side of the equation, it appears in 2 things on the right. And so you should make sure that you have got the right number of each of those products on the right-hand side exactly right first, which you're doing using the carbon and the hydrogens from the alkane, and only then should you look at the oxygen and look at balancing the oxygen. So at the moment on the left, we've got 2 oxygens, and on the right, we've got 2 plus 2, so that's 4 in total. And whilst this is going to look a bit daft, and this obviously is not what you would write for your final answer, however, whatever number of oxygens you add up, so 2 and 2 is 4, then what you can do is you can write that as a fraction. You write whatever that number is over 2, and that is your correct number of oxygens. Now, you can simplify that. 4 over 2 is clearly 2. So I can just go ahead and do that. But when we've got something where you've got half a mole of oxygen, then I find that it's quicker and easier to check things if I do it over 2. So let's give an example. All right, so let's do another complete combustion equation. So this time we're going to do a much larger molecule. We're going to do octane. Okay, I'm not going to bother with the state symbols here because it's just about the balancing. So obviously we're doing complete combustion, so I'm going to get carbon dioxide and water as my products. And then if I talk you through balancing it, I'm going to start with the carbons. I've got 8 in my octane. I obviously only have 1. So whatever this number is after the C is what I'm going to put here in front of the carbon dioxide. So I'm going to put 8. And then whatever number of hydrogens I've got in my alkane, I'm going to put half that in front of the water, half because I've got H2. So I'm going to put 9. So now I'm going to add up my oxygens. So I've got 2 times 8 is 16, plus 9 is 25. So my number of oxygens is going to be 25 over 2. Now I can make that 12.5, but personally I prefer, for my own personal benefit, I prefer the 25 over 2 because it just means straight away when I'm rechecking it later, I know that I've got 25 oxygens. So what happens is those 2's will cancel out when I'm actually doing the sum. So that's our complete combustion, pretty straightforward. The only other thing to say is that it's very exothermic. Okay, and that's useful because when we're talking about fuels, because that energy being transferred is the energy that we're then going to use usefully. Okay, so it's very exothermic. So that's complete combustion. We've also got incomplete combustion. So let me just bring that up. Now, when we look at incomplete combustion, the difference here is basically it comes down to the products. H2O is always formed. So that's no different than complete combustion. But the difference is it can also, plus it's going to be either carbon monoxide, and I'm going to put and or, because it could be either of these depending on the equation, or it could be one of these. So we've got carbon monoxide and or carbon. So this is toxic, or very toxic in fact. Now in chemistry, if you ever feel that when you're giving an answer and you feel that you're using, or you want to use the word poisonous or poison, please don't use that. Please use the word toxic. So if you ever feel the urge to use the word poison or poisonous, please use the word toxic. So that's a very toxic gas. That's carbon monoxide. And then what we've got with carbon, that is essentially the way of thinking about it is soot. Okay, so it's a solid, right? So it's important to remember that's a solid. So again, I'm just going to do just 2 example reactions. I'm just going to do them both with methane. One is if it's forming carbon monoxide. One is if it's forming carbon or soot. I will put the state symbols this time for this particular one. So we've got methane. And that's obviously a gas, and it's reacting with oxygen. So that's a gas. I'm going to leave the balance for the moment. Now I'm making carbon monoxide in this example, and I'm making water because we always get water. If I look at it, I've got 1 carbon and 1 carbon, so I don't need to change anything there. I've got 4 hydrogens and currently only 2. So I'm going to put 2 in front of that. Now I count up my oxygens on the right. I've got 1, 2, 3. So I've got 3. So I'm going to do it as my fraction because I find that is easier. So 3 over 2, or 1.5. Now if it's soot, so again it's methane. again, it's oxygen. Got to remember that my carbon that's being produced here is a solid. So that's the smoke that you see. So when you see smoke, when you're burning, if you're burning a fuel and you see smoke, then that will be the carbon. So there'll be incomplete combustion happening there. I get water, like I always do. Obviously, my waters have to be balanced the same because I've got the same number of hydrogens. My only oxygens are in my water. I've got 2. I've already got 2 here, so there's no need to put anything in front. The only other thing to say here is that as well as producing either a very toxic gas and or a particulate, which is not very good for respiratory, but also isn't very good for engines because that can start to clog them up. So even leaving aside those issues, another reason why incomplete combustion is not something we favour is because the actual reaction itself is less exothermic. So we're getting less energy transferred to the surroundings, so we have less useful energy basically going on here. So that deals with our incomplete combustion and complete combustion is, in terms of chemical reactions. So we finish with our pollutants from burning fossil fuels. So I'm just going to talk through just some of these things. So you can always pause the video and just have a look at each of these individually, have a look at the table. A number of them are to do with complete or incomplete combustion. The ones I just want to pay a little bit more attention to are the sulfur dioxide and the nitrous oxides. So I'm just going to start with the nitrous oxides. So when you did the chemistry of the atmosphere at GCSE, one of the things was that you may have been aware of prior to this, but anyway, one of the things you may have noticed was that there was the most abundant gas in the atmosphere is nitrogen, nearly 4/5. And one of the reasons for its abundance is the fact that it's very unreactive. And we can now think about why it's unreactive, because if we think about, you may have even done the dot and cross diagram at GCSE, but if you think about the bonding between the nitrogen, we've got a triple bond, right? A triple covalent bond. So it's very strong. So a lot of energy would be needed to break that triple bond. So nitrogen is very inert or very unreactive. I wouldn't say it was inert, sorry, it's very unreactive. Now, when a car or combustion, anything that's got a combustion engine, but let's just say a car for the moment, the oxygen that is there to combust with the fuel for hopefully our complete combustion, that comes from the air. So the air from the outside is coming into the internal combustion engine to provide the oxygen for our complete combustion. However, what we've also got coming in is a lot of nitrogen, and a lot of energy is being released through the complete combustion of our fuel, and that now some of that would provide enough energy that would be enough of an activation energy to get nitrogen from the air that's come into the combustion engine, that nitrogen in the air, to actually react with oxygen. So it's at very high temperatures, i.e. there's the energy that would be required to make that happen is being supplied, and so the reaction is taking place. So the last thing I want to look at now is the production of sulfur dioxide and how we remove it. So our fossil fuels have come from organic matter. So as well as our hydrocarbons, we're actually going to have compounds that have sulfur in them. And so when those compounds combust, we're going to get sulfur dioxide produced. Sulfur dioxide, if it gets into the atmosphere, can eventually lead to acid rain, or it makes the rain more acidic. So one of the things that we want to try and do is to remove that, and we want to remove it before it gets into the atmosphere. So the way that we do that is that the gases are passed through it's called flue gas desulfurization, but they're passed through what's called a scrubber. And so that sulfur dioxide is then reacted with either calcium oxide or calcium carbonate. So if I just scroll down a little bit, and what we'll do is I'll just highlight the fact it's the sulfur dioxide, and we'll just write a couple of equations to show those reactions. So if it was calcium oxide, it would be reacting with a sulfur dioxide, and it would be making CaSO3. Alternatively, we could be using calcium carbonate, again reacting with a sulfur dioxide, again forming CaSO3, but we would also get carbon dioxide as well. Now, they can sometimes ask you what type of reaction is this. Now, this is an acid-base reaction, so they're both acid-base reactions, and that's what you would say in terms of what type of reaction it was. You'll understand this a little bit better when you've finished the course, but a rule of thumb is that metal oxides are bases and non-metal oxides are acidic. So what you've got here is essentially a base and an acidic gas reacting together, and it's called an acid-base reaction. So the SO2 is an acidic oxide in effect, and the product, this calcium sulfate 4, that's also known as gypsum, and that can be used to make plasterboard, but that's not really terribly important. But what is important is that how do we remove, questions can ask us, how do we remove sulfur dioxide? You need to know one of these two reactants, calcium oxide or calcium carbonate. You need, whichever you choose, you've got to remember or be able to work out what the reaction would be, and you need to remember that it's an example of an acid-base reaction. And that is it for alkanes, other than the chlorination of alkanes, which is in the free radical substitution video. So I hope that's been useful, but do let me know if you've got any queries or comments.